Okay. You see, this expression we have over here is true in general, whatever the temperature is. The only thing we actually assumed in this derivation is that B was small. And eventually we took the limit that B goes to 0. So in particular, it's also, this expression is also valid at large temperature limit, not just a small temperature limit. Now at the large temperature limit, we had already seen that Z is much, much smaller than 1. So we can just go ahead and you see this is at large temperature. This is what Z is. Remember, this is e to the power beta mu. So mu is just kt times logarithm of lambda cube over gv. Or this is kt times a logarithm of n plus other terms independent of n. So mu 0 of xn in this case just turns out to be kt logarithm of x times n. If you take its derivative with respect to x, evaluate that x is equal to 2. This is kt over x evaluated that x is equal to 1/2, sorry. 1/2, and so this is twice kt. So the magnetic susceptibility is just 4 mu star n over kt. Now this 1 over T result was also one result that we had obtained for the classical gas. So now we have the magnetic susceptibility at small temperature, at large temperature, at small but finite temperature, so you can do whatever you want. Now let's look at, again I repeat here, in this case this is chi was larger than 0. So when you create apply a magnetic field, you create a magnetization in the same direction as the applied magnetic field. So this is what we call the diamagnetism. And it's caused by the alignment of the magnetic dipole moments in your system. In this case, they are the magnetic dipole moments of the electrons. Now the alternative would be there's also a paramagnetism. You see, here the idea is as follows. You have, if you put some charges in a magnetic field, charges that are moving, they will start going on circles. Their orbits will be circular. Or the same phenomenon, actually, it is paramagnetism, also happens in ordinary material. You have the atoms. In the atoms, electrons are going in circles. Now, the problem is if you put these in a magnetic field, basically they will be feeling a changing magnetic field. And since they will be feeling a changing magnetic field, their speeds will change. Due to this change in the speed of the charges, there will be an additional induced magnetic moment. And this additional magnetic moment, as we will show now, turns out to be in the opposite direction of the applied magnetic field. So that's what we will be, well, that's the origin of this paramagnetism. Now, before studying the paramagnetism, I mean, we don't have too much time to study all the derivations. Let's look at this system of electrons in a magnetic field. Today we can look at this problem, and tomorrow we will be studying its magnetic properties. So you see, if you have a magnetic field, let's say, we have a system. The electrons are moving, they are not at rest. So if you have moving electrons in a magnetic field, let's say, assume that B is, let's say, in this direction. Now their orbits will be circular. And which direction will they circle? Clockwise or counterclockwise? Mm-hmm. How did you obtain it? Let's say
moving in that direction.
Let's say in this direction. Will it feel a force, upward force or a downward force?
Yes. In this direction.
Upward force, right? More or less upward. Then it's just moving clockwise. This is the force.
Mm-hmm.
So they will be basically going clockwise. So these will be the orbits. Well, this is a three-dimensional problem. Let's say the Hamiltonian of the system will be P minus Q over C A being the vector potential squared times 1 over 2m. This is it's just free electrons. Now, classically, the electrons should go around clockwise orbits. And of course, there, let's say, if we think of this as a three-dimensional problem, there is the z motion. Z velocity is independent of b. So there is the energy of the system will be pz squared over 2m plus energy of the rotational motion. Whatever that energy is. So its trajectories will be helices. Now for the time being, let's separate the problem into two, the z component and the xy component of the speeds. In the xy component, we have this circular motion. We can actually use the Bohr's quantization condition. It gives a reasonable answer. So do you remember the Bohr's quantization condition? So the Bohr quantization condition for circular orbits, it's also used for the atom, is basically the circumference of the circle, of the orbit, should be an integer multiple of the de Broglie wavelength. Or 2 pi r should be equal to nh over mv. And then we have the other condition that the centripetal force, which should be mv squared over r, this should be given by the electromagnetic Lorentz force. So this should be q times v times p. So we have these two conditions for the orbits. Well, let's simplify this one. So this tells me that v should be equal to qb over m times r. So if I just substitute it over here, 2 pi r should be equal to nh over m. 1 over v is m over qb times r. M's will cancel. So this is equal. This tells me that r squared should be nh bar over qb. These are the possible radii of my system. Now, what is the energy of this system? Or let's see, 1 over 2 mv squared, the kinetic energy. This is equal to 1 over 2 m qb over m squared times r squared, which is 1 over 2 m times QB over M squared, well, R squared is N H bar over QB. So this QBM cancels one of these, so the energies of these states of these electrons are quantized. H bar. Okay, let me make a change of a couple of changes to match the units. So in your book, the units with the units used, there is a factor 1 over C over here. So there is a factor C over here, and there is a factor C over here.
It becomes C squared. Then it becomes C squared, I said.
Let's see.
C was on that.
Is there V is there's a C over here. R in R squared. So here there is a C. R squared is this one. So in R squared there is also another C. There's another C over here, so that also cancels one of these C's. Well, of course, this is a very crude approximation. If you solve it properly, it just turns out that the energy levels are quantized. This is EH bar B over MC. J plus 1/2. So the main difference from this result is that n turns out to be not just any integer, but just an odd number of odd integers. So this is the correct answer for the energy. Now let's see. Another interesting feature is, let's look at this one. So these are the possible areas. Now pi r squared, which is the area of the orbit, is just n times pi h bar c over qb. And the flux going through the orbit of the electrons is just pi r squared times b. Well, this is n times pi h bar c over q. This is also quantized in terms of some unit flux. So the total flux can be just a multiple of the unit flux, or flux passing through the closed orbit of an electron. Now, what is the minimum area of this orbit? Well, the minimum area of a single electron. This is pi r min squared. This is pi h bar c over qb. In an area of Lx Ly, how many of these orbits can fill? Well, just Lx Ly divided by qb over pi h bar c. So this should basically be the degeneracy, more or less, of this orbit. So you see, we have these electrons, okay, their energy levels are quantized, but nevertheless, it can be orbiting around this point, or some other point, or some other point. So all these states, they will be different states, if they are at least separated well enough. We can definitely say that they are orthogonal to each other. They are different states, but nevertheless, they have the same energy. So we have this problem of almost infinite energy.
Did you multiply area with Lx, Ly?
No. You see, what I did was, I'm assuming that my system has, that all of my system has size Lx and Ly. Each one of these, there's a kind of an area quantum, let's say, pi r squared.
Mm.
This you can say, in quotes, our area quantum. How many of them can we fit within my area, Lx, Ly? This is my total area, Lx, Ly. I just divide it by my area quantum, QB over pi h bar c.
It's not the area.
No, you see, I'm just, okay, let me just erase this. I'm dividing by pi times r min squared. So essentially, I have these many states having the same energy.
Then you had a mistake over there. The result should be
oh, yes.
2b times.
You're right. QB times pi h bar c. Okay. Typically, this should be the degeneracy of my states. Now, okay, let's try to calculate this. I mean, eventually, for our treatment of the system, we will need the degeneracies. So remember, if you want to calculate the partition function, I have to sum over all the microstates. But rather than summing over the microstates, I can sum over the energies and multiply the energies by its degeneracy. How many states are there with that energy? So another way of looking basically at the same problem is, so you see, if there is no magnetic field, the energies form a continuum. Let's say epsilon xy. So I'm just writing the total energy of my system as pz squared over 2m plus epsilon xy. And this epsilon xy, in the case of b is equal to 0, is basically px squared plus py squared over 2m. And in the presence of b, this is just E h bar b over mc j plus 1/2. It's basically there should be some kind of continuous transition between these two limits. And I can just gradually increase b. Nothing will change. Nothing should change. Unless there is some kind of a phase transition at b is equal to 0, everything should change continuously. The number of states should kind of change continuously. So what is actually happening here is, you see, I have all these energy levels. And when I turn on the B field, there is an energy level over here, another energy level over here, another one over here. They are spaced equidistantly. So you can think of this process as more or less, let's see, let me just put the mid levels. As you increase B, what happens is all the levels within this range, they become degenerate. And similarly, all the levels within this range, they become degenerate. etc. So that's basically what the effect of the B field is, kind of just cause the various states to become degenerate in the presence of the B field. Then to calculate this number of density of states, we can basically count the number of states over here. Well, I know how to count those numbers. If I sum over all px, py, such that px squared plus py squared over 2m is less than eh bar b over mc times j plus 3/2, no, j plus 1, and larger than eh bar b over mc times j. I just added 1/2 to the energy level below and the energy level at that energy level so that I get the mid levels. Well, this sum is the dx, dy, dpx, dpy over h squared, which is, well, dx dy just gives me Lx Ly, and I have, if I go to spherical coordinates, I have 2 pi p xy dp xy, the magnitude of the momentum in the xy plane. This is divided by h squared. Lx Ly 2 pi over h squared pxy squared evaluated from 0 to, no, not 0, pxy is 0 squared to, or let's say j, to pxy j plus 1 squared. So this is equal to Lx Ly 2 pi over h squared. Now pxy squared is just px squared plus py squared. And this, if I put the limits, it's basically taking the difference of these two limits. And that becomes eh bar b over c times 2. Let's say aj, the degeneracy of the state that has the quantum number j, independent of j. So aj is Lx Ly. Well, this is h 2eb over hc. Now let us just compare it with my previous result. Even the previous interpretation, the previous kind of intuitive interpretation, let's say, just gives the correct answer. Now that I know the degeneracies, I can just go ahead and calculate the partition function. Let's say for a single let's just do. So sum over single particle states of let's say e to power minus beta epsilon. This will be sum over j from 0 to infinity. Well, the energy there is the Lz dpz over h. This is the z momentum. For a given j, my degeneracy is Lx Ly 2Eb over hc, and then I have the exponential of minus beta e h bar b over mc j plus 1/2 plus pz squared over 2m. Now I know how to make those sums. And once I know how to make those sums, I can just calculate whatever partition function I'm interested in, and then I will be done. Okay, this we will continue tomorrow. Any last questions? So see you tomorrow.